Good evening, everyone. I'm Anish Ambekar, PMRF and PhD candidate from Aerospace Engineering ISC Bengaluru. Welcome to Week 11 tutorial for the NPTEL course Solid Mechanics. This course is being conducted by Professor Ajit Kumar. In this week, Professor Ajit covered concepts of influence coefficient, generalized displacements, reciprocal relation, then Maxwell-Betti-Rayleigh reciprocal theorem, Castigliano's theorem, as well as energy stored in a beam. And then he went on to show how these energy methods can be used for certain problems which may not be possible to solve using simple Euler-Bernoulli beam theory or Timoshenko beam theory. With that in mind, we'll look at this week's tutorial problems. The first problem, it's a simple true or false question. This given statement is energy method is used to find deformation in those bodies in which stress equilibrium equations are not valid. So we start with energy method by first looking at what stress equilibrium equations are, and from there on we move on to proceed that since our stress equilibrium equations are valid and they are linear in stresses, and then you have linear relation between stress and strain, and if you also have and from there you also have strain displacement relations which are again linear, so you end up with a case where your forces would basically be linear with your displacement. So energy method actually starts off at the very beginning. We consider the stress equilibrium equations itself, so though they are the fundamental foundations. So this given statement that the energy method is used for bodies in which stress equilibrium equations are not valid is wrong. The stress equilibrium equations are going to be valid. So this statement is false. Problem number 2. Why are stress equilibrium equations linear in unknown displacements? So as I mentioned earlier, you initially stress equilibrium equations should look something like dou x, dou sigma xx by dou x plus dou tau y by dou y plus dou tau xz by dou z plus bx equal to rho x. This is how stress equilibrium equation would look like. And so what we have after this is, if we use linear stress strain relation, and you combine that with, you have to further combine that with linear strain displacement relation. Linear strain displacement relation. So once you use this two equations combined with the above stress equilibrium equation, your essentially overall equation becomes linear in displacement. So to go through this transformation, you need linear stress strain relation as well as linear strain displacement relation. So options A and B. The third problem. Consider a deformable body clamped at some part of the boundary. Forces F1 and F2 act on the body at two different points. The energy stored in the body due to force F1 will be proportional to. Okay, so we are asked about a deformable body. So draw a deformable body. Just say clamped at the left end like this, and you have got a force F1. Label this point as 1. So you have got force F1 acting here and force F2 acting on this point, which is the point number 2. And we are asked what is the energy stored in the body due to force F1. So as you know, the energy that will be stored in this body due to force F1 would be half F1 delta 1, where delta 1 is displacement of So it's actually corresponding displacement of force F1, which would mean that delta 1 is in same direction as F1. Okay, so this would be displacement. This would be the energy stored is basically proportional to delta 1, which is nothing but the displacement of point 1, which is the point where F1 is applied, and delta 1 needs to be in the direction of F1. So F1 is applied vertically downwards, delta 1 will also be measured vertically downwards. So why this is the case? Because suppose I take, because I'm looking at energy stored in the body, when I'm applying some external force F on the body, an internal force F internal will be generated, and it will be acting along the line of F1 itself, and when it will be acting along F external, which is the external force, and suppose for some reason the overall displacement of the body at this point is, say, delta it's delta, which is nothing but delta parallel plus delta perpendicular. So your delta is equal to delta parallel plus delta perpendicular, correct? And if you look at the work done by the body, it would be like F internal dot delta, which should be nothing, integral of dot d delta, which would be nothing but, this is the work done, this is the energy stored in the body, which is nothing but F internal into d of delta parallel, because since we are taking the dot product, if we only want the component along the direction, so the energy, again even from this logic also, energy stored is only along the if you want to calculate the energy stored in the body, you only want the displacement which is along the applied force. So option B. Problem number 4. Influence coefficients can relate. So in general, you have what delta I is equal to Kij Fj. This basically relation says that if you have, say, different forces F1, F2, M3 and so on, where all the way till say Fn, this particular relation delta is equal to Kijfj gives you the relation between displacement at the point I and the force which is applied at point J. While we initially began by defining this for a force displacement relation, this particular equation is valid for generalized forces and displacement. So what are generalized forces? Generalized forces would be nothing but force comma moment, whereas generalized displacements would be nothing but displacement, whereas generalized displacement would be nothing but displacement and rotation. So influence coefficients can in theory relate any of these with any of these. So you could have a force displacement relation, you could have a moment displacement relation, you could have a force rotation relation, as well as a moment rotation relation. So influence coefficients can be defined for all these 4 cases. Problem number 5. Select true or false. By reciprocal relation, we know that K12 is equal to K21, where K12 and K21 represent influence coefficients. If K12 relates force and rotation, and K21 relates moment and displacement, then only the magnitude of K12 and K21 are equal and not the units. Okay, so K12 relates force and rotation, right? So I would have to plot, say, point 1, point 2, and I am told that there is a force F1 which acts, there's a rotation theta 2 which is happening at the point 2, and K21 is the other way around, where you have a moment M2 and you have a displacement, delta 1, displacement delta 1. Okay, so this is what we are given, and by reciprocal relation we know that k12 is k21. So reciprocal relation kij is equal to kji. This holds true for the generalized definition of influence coefficient, where either of force or moment can be related to either of displacement or rotation, which is exactly what is happening here. K12 is a force rotation influence coefficient, whereas K21 is a moment displacement influence coefficient. But if you look at their units as well, you would get K12, unit of K12 is equal to unit of force 1 upon rotation 2. The unit of rotation is simply 1. Rotation doesn't have any units, it's radians. So no units, whereas force has an force has the the units of Newton in SI case, which is nothing but kg meter per second square. This is how we are representing the dimensions of K12. Similarly, if we look at K21, it's nothing but m2 by delta 1, right? So which should be, I should write this as divided by 1, which is nothing but m1 l1 s minus 2. Moment is Newton into meter, so that would be m2 l1 s minus 2, or t raised to minus 2. I should write for time rather than second. Yeah, t raised to minus 2 upon m, which is nothing but m1 l1 t raised to minus 2. Therefore, we can see that not only their magnitudes are same, but they are actually same in terms of units as well. So this given statement which says that only their magnitude is equal but their units are dissimilar is wrong. So this statement is false. Problem 6. Shear energy due to transverse load is given as V square by 2 kGa. So this is the shear energy that is, you can think of this as the shear energy which is given in like one cross section of a beam. So if this is my beam and some loading is applied with some moment and whatever, so this beam would store some energy, and the energy that is stored specifically due to the transverse shear load V on this cross section would be nothing but V square by 2 kGa. Here K is the shear correction factor that you have coming out from Timoshenko beam. So none of these. Problem 7. Suppose we want to obtain displacement of a point on the free surface of a body using energy methods. Which of the following statements holds true in this regard? So the first statement is we cannot find such displacements as we will encounter division by 0. The second, so okay, before I go through the statements, I'll just draw the diagram. You have a body like this. Okay, sorry, you have a body like this, and suppose you want to point, this is a free surface, this is a point on the free surface, and you have some loads f1, f2, all the way, right? F3, something like that. You have got multiple loads between f1 to f, these can be moments also, and you have a point on the free surface. So by free surfaces, it would mean that this is a point on the outside of the body which has no force acting on it, no external load acting on it. So this is the point. I'll just name this point as, say O. So is a point on the free surface, and you want to find, we want to obtain the displacement of this point. So what the approach would do is, suppose you take a force P. I write PV because here V is like In a sense, I'm saying virtual, but not exactly. We assume a force PV to be acting on the point O, which is where we are looking at, which is the point on the free surface, and we calculate. So you, for this particular this thing, you do something called calculate the energy of body. So we know how to calculate the energy of the body for in the case of a beam. Suppose this particular problem is for a beam, and you want to say for this particular point, say oh, this is O. I'll assume some load PV here. Suppose it's vertical, and this is the externally applied load F. I'll assume this PV, and then using this PV, I'll go on to calculate the total energy stored in this beam due to both the applied force as well as what I'm calling the virtual force. So once I've calculated the energy of the beam, what I'll do is I'll apply Castigliano's theorem. So if you want to use, if you remember what this is, it would basically give you delta O is equal to dou energy of the body upon dou PV. Right? This is Castigliano's first theorem, which we looked at in the class as well. And once you have that, what you do is you do one more thing. You set PV to 0 in delta O of PV, comma F1, comma F2. So this is what you obtained from here. Delta naught as a function of your virtual force acting on that point, then F1, F2, and so on. And now that we have chosen this, now that we have obtained delta O from Castigliano's theorem, we are since there is no PV actually acting, or the point O is a point on the free surface of the body, we set PV equal to 0 in this delta O equation, and you essentially obtained your delta displacement for the free surface point O. So this is the way to go about it. So which of the options is true in this regard? Yeah, the last option. We can find the displacement by considering a dummy force. So this is basically what I called as the virtual force PV acting on that point, which is point O. And this displacement delta naught is nothing but E body by dou PV. Problem number 8. Consider a spring mass system. The equation for displacement of the mass x denoted by x is given as m dou square x by dou t square plus kx equal to f of t. Here f of t is the applied load. Which of the following holds true? So we are given this equation m. So this equation is nothing but mx double dot plus kx equal to f of t, and we are asked if this equation is linear, non-linear, or anything like that. You can straight away observe that this whole equation doesn't contain any terms of, so no terms of say x raised to n with n not equal to 1. You can straight away see that there is no x square x cube or root x or cube root x or something like that term coming on this equation. So if you simply have mx double dot plus kx equal to f of t. Now f of t is the externally applied load. So if I want to check if this equation is, if I want to study the nature of this equation, like whether it's linear or non-linear in x, we ignore the externally applied term, so we ignore the external load. So my equation without the external load would look something like mx double dot plus kx, right? This is my equation without external load, and once I have this, I essentially look at what E of x1 plus E of x2 would look like. So E of x1 plus E of x2 would look like m x1 double dot plus kx plus m x2 double dot plus kx2 is equal to 0 plus 0, which is nothing but 0. So your equation becomes m x1 double dot plus x2 double dot plus k times x1 plus x2 is equal to 0. Again, with external load, this whole equation would look like m x1 plus x2 whole double dot plus k times x1 plus x2 plus f equal to f of t. This is how it would look like with the whole external applied load. But you can see that this is nothing but an equation in x1 plus x2, right? This is an equation in x1 plus x2. So your given spring mass system is so if x1 is a solution that satisfies your given spring mass system and x2 is another solution, then any solution of the form ax1 plus bx2 can be shown to be also a solution of your given spring mass system without any externally applied load. So this equation that you have is linear in terms of x. To determine this equation that you have is linear in terms of x. Problem number 9. Consider 2 points x1 and x2 in a body clamped at some part of the boundary. In one scenario, we apply forces 2 Newton and 4 Newton horizontally at x1 and x2. The horizontal displacements at 1 and 2 are 1 cm and 4 cm respectively. In another scenario, we apply forces 4 Newton and 1 Newton horizontal at x1 and x2 respectively. The horizontal displacement of x1 is 3. Find the horizontal displacement of x2. So I am drawing it like a body like this, and this is my x1, this is my x2. Forces are f2 delta 2, f1, and the displacement delta 1. We are given some values for force and displacement. So in this case your delta 1 would be k11 f1 plus k12 f2, right? This is the displacement of point x1. Similarly for point x2 you would have delta 2 is equal to k21 f2 plus k21 f1 plus k22 f2. Suppose we only look at point 1 in both the cases, then we know that in case 1 displacement 1 is nothing but k11 into f1, which is 2, plus k12 into f2, which is 4, which would imply that half is equal to k11 plus 2k12, which would mean that k11 is half minus 2k12. Similarly, from the second case, horizontal displacement at a point x1 is 3, which is equal to k11 into 4 plus k12, which would mean that k12 is nothing but 3 minus 4k11. If we use these two equations, we basically get k11 is equal to half minus twice of 3 minus 4k11, right? This is nothing but half minus 6 plus 8k11, correct? If we just rearrange, this becomes 7k11 is 6 minus half, which is nothing but 11 by 2. So k11 is 11 by 14. K12 is 3 minus 4 times 11 by 14. We have 14 3s are 42 minus 44, which is minus 2 by 14. If we look at the point number 2, in first case, displacement is 4. So 4 is equal to 2k21 plus 4k22. But from reciprocal theorem, we know that k21 is equal to k. From reciprocal relation, we know that k21 is nothing but k12. Therefore, if I want to simplify this, I would write 2 is equal to k12 plus 2k22. Therefore, k22 is 1 minus k12 by 2, right? K12 is, this would be minus 1 by 14. So 1 plus 1 by 14 is 15 by 14, right? 1 is k12 by 2 plus k22. Yeah. So k22 is there, and now we want to find displacement of x2 in case 2. For case 2, this x2 would be displacement delta 2 is k12 into k21 into f1 plus k22 into f2. K21 is nothing but k12, which we know here. So my delta 2 becomes minus 2 by 14 into, what is my force? F1 is 4 plus k22 is 15 by 14. What is my force here? It's 1. Yeah, it's 1. So I got minus 8 by 14 plus 15 by 14, which is nothing but 7 by 14, which is nothing but 0.5. So my horizontal displacement of x2 becomes 0.5 centimeters. Problem number 10. For the data in problem 9, find the displacement of x1 if horizontal forces are 1 Newton and minus 1.5 Newton. So delta 1 is nothing but k11 f1 plus k12 f2. In this case, f1 is 1, so it's k11 minus 1.5 k12. What is k11? K11 is 11 by 14 minus 1.5 times. What is k12? It's minus 2 by 14. So it's 11 by 14 plus 3 by 14, which is nothing but 14 by 14 equaling 1. So we have also found the displacement for this particular point. That solves this problem as well. So that's all I have on my end for this particular week. Next week we'll look at some problems for failure methods. That is the last upcoming tutorial. So if you have any doubts from any of the classes so far, make sure to attend that and make use of that. Thank you.